Hello everyone. Good evening. I hope you can hear me. All right. So welcome everybody to the fourth session of Foundations of Our Software course. And so I hope you've all already watched the fourth week's videos, right? Because these live sessions, they would be more useful if you have already watched the lecture videos, and so that right, so you already know mostly what has been discussed. So if there are any questions, then you can ask those, and then we can just clarify that. All right. So so let me just start sharing my screen. And yeah, so can you just confirm if you can see my screen? I hope you can see the screen. Just any one of you, can you confirm? Uh, Hi, can you hear me? Yeah, yeah, you can see. All right. Okay, thank you so much. All right. So, all right. So you have all, most of you, I can see familiar names. So you've all been in this, attending these sessions before. So we are done with 3 sessions. This is the fourth one, and the Zoom link stays the same. You already have access to these links, YouTube link and the Google Drive. And I hope by now you've all tried to install R and R Studio. Right? These are just placeholder slides, if you want to refer to it. And so this is where we would be headed now. So before I start discussing this week's topics, there was one question which was remaining from the last week's discussion. So this was mainly pertaining the modulo and the quotient or the integer divisor thing. So I will just uh, give you a quick recap of, sorry, give you a quick recap of what we discussed, where we were stuck last time, and then what is the way out. Yeah. So I'll just connect this. Yeah. All right. So what the modulo and the quotient or the integer function does. So let's say we want to divide 10 by 3. All right. So now you have 3 here and this. So this becomes your quotient and this becomes your remainder. All right. And now what is, so here, let's say you were dividing, so let's say x is equal to 3 and y is equal to 10. Right? So what step you were doing is that you were dividing y by 3. Now y, y divided by x, right? So now the thing is that x multiplied by this quotient here, so q, and to that, if you add the remainder, that should give you y, right? I would like you all to, if you can just keep saying yes, you understand that, so that I know that this is understandable. Yeah. So this is the basic funda of
Yes.
yeah, this is the basic idea. Now what is, so now in addition to, so once you have the quotient here, so when we are normally dividing this, right, this would have given us 3.33 and so on. Now what you can do is, so if you remember the last time we talked about something called the floor and the ceiling also. So floor is basically giving you the truncation. The floor function is giving you the uh, highest integer before this, right? So floor of y by x, that's going to be 3. because 3 is the integer which is just below 3.33. Now that is going to be your q here, right? And whatever remains, that's the remainder. Now, keeping this in mind, we'll see the examples when either x or y is negative, because that is where we were having the confusion. Understanding it for numbers where both of them are positive, that's relatively simpler. All right. So I have a few examples in R, so we can quickly go through it. Okay. Yeah. Yeah. So I hope the screen is visible. Yeah, this is, I mean, it's loud, not it's large enough to see. Yeah, so this is what it was. Okay. So let's take the example, x is 100 and y is 3. All right. And so what basically we want to do is this thing. So this symbol, %/%, that gives us the value q, or the quotient, and the %%, it gives us the remainder, right? This is what you had seen in the last week's lectures. Now, so this is what I just told you, that the quotient is always going to be the result of floor, right? Of the normal division. So here x by y, it would have given us 33.33. And if I do floor x by y, it's going to give me 33. And that is actually what is going to be, so just to explain, these values of quotient and remainder you can find out in two ways. One is by this actual operator that we discussed in the last week, and the other thing is by the actual, by the logic also, that the floor of the two of that division is going to give you the quotient, and then this thing, right? So the quotient multiplied by the divisor, and if you subtract that from the dividend, that larger number, you should get the remainder. So I would like you to take a look here. So I'm going to compute these four values for the case that we are looking at, for x and y equal to 103 respectively. If we find out this, so you would see q1 and q2 should be the same, and r1 and r2 should be the same, right? So if I'm selecting the whole thing and I'm just running it, so you can see in this case, your quotient turns out to be 33 and the remainder is 1. So this means our logic is fine. So now we can take some other examples. So now let's say if x is 100 and y is -3. All right. So now the thing is, now x divided by y, it gives us -33. So can you tell me what is the number, what is that integer which is just less than -33.33? What should be the result of this thing? Floor x by y. You're not audible. Can you be slightly louder?
-34.
Yes, that's correct. So it's -34. You remember number line? So when you have minus numbers, the number less than that is going to be farther away from 0, right? So you would see that when you compute this, it's Q2 becomes -34. And that is also going to be the result of this thing, right? So this function is also going to give you -34. And now if you compute R1, so the thing is that, I mean, the remainder that should satisfy this value. So 100 minus, so this number that we just calculated. So -33 multiplied by -34. Sorry. Q2 is, yeah, so y is 3. So -3 multiplied by -34, right? So that's 102. And x is 100. So 100 minus 102, right? So that's going to give us -2. So therefore, when you see this, your R1 and R2, or the remainders in either way, that becomes -2. Getting the thing? So this is simpler to imagine, right? This is more intuitive. The value of x by y, you know what it is going to be. You find out you find out the integer which is just below that. So you do you find out the value of floor, and then you know that this equation uh, needs to hold, right? So the divisor multiplied by the quotient, and if you add the remainder to it, it should give you the dividend back, right? So this funda is what is going to help you. So we can take any of these cases. So I've just made a lot of things here. So x by y, where x is minus 100, both of them are negative. So, and then of course, then the other way. So if y has a higher numeric value, so y is 100. So we can take one more case. So floor is the value load. So 3.33. So what is the integer just below 3.33? That's 3, right? So if I write it here, so if I just draw the number line, okay, this is 0. Let's say this is 2, this is 3, this is minus 2, and this is minus 3. Now, and let me also just draw one here. Okay, so this is my number line. Now, if I have a number here, let's say it is 1.7. So what is the integer just below this? That's the integer, right? And like you said, 3.33. So what is the integer just below it? It's 3. Likewise, if I have, let's say I have minus 1.7. So the integer just below it is minus 2. Below means just less than that. So we go on the negative side, right? And likewise, if we have something like minus 3.33, so it's going to be minus 4. Yeah, all right. Okay, so that is how you're going to calculate floor. And so to understand what the remainder is going to be, you can just fit. So this equation you understand, like this is how division works, right? So I hope this clears the last week's case. So I will anyway share the script with you. So these cases are going to be there. You can try this also. But yeah. So I will now start with today's ceiling means the next number. So it's going to be U shift right. What is the shortcut key for increasing or decreasing the font? So it's going to be control and plus, control and minus. Yeah. And if it's Mac, so it's going to be command plus, command minus. And yeah, ceiling is the number, the least greater integer, and floor is the highest lesser integer. All right. Okay. So now just a couple of things before we start the actual, we go into the R codes. So I would like to tell you a little bit, since I think we can spend some time on this today. So I would like to talk about matrix multiplication. For integers, what would be the floor and ceiling? It would be the same number itself. Good question. Okay, so floor, so 357 is going to be 357 itself, right? Because that's the number, right? So just a second. Okay, maybe I'll just, since we are completing this thing. So you want to try floor and see 3, 5, 7, right? That's what you would like to know. So if I press enter, it's going to give me the same numbers, right? Because so basically what this statement means is that I want to find the floor of these 3 numbers, which is 3, 5, and 7. Now 3 is the integer which is just below it. So for integers, it's the same thing, right? Yeah, just a second. Okay. So I hope that's what you were asking. Yeah. Okay. Okay, so I will quickly go into matrix multiplication now. So now I'm just taking the example of 2 by 2 matrix because that's the simplest to understand. But there are a lot of things about matrices that, so there are a few things I will generalize here so that you are not confused by just, 2 by 2, which is a lot of things may be specific to 2 by 2 matrices, but we would like to generalize it because uh, that's what is, that's what you would like to learn here. So, as you know, for matrices, for anything which has 2 dimensions, we first refer to the number of rows and then we refer to the number of columns. So here it has 2 rows and it has 2 columns, right? So therefore here we are writing it's a 2 by 2 matrix. Likewise, I'm taking another matrix. This is also 2 by 2. Now, if two matrices have to be multiplied, so let's say the matrix is M cross N. So M rows, N columns. And I would like to multiply that matrix with another matrix that has, let's say, N into P, right? So this is allowed. These two matrices can be multiplied. So the requirement for matrix multiplication is that these two numbers, so the column in the first matrix, number of columns in the first matrix, and number of rows in the second matrix, that should be the same. And when you multiply these two matrices, the resultant matrix that you get, the dimensions of it is going to be it's same as, it'll have number of rows same as the number of rows in your first matrix and number of columns same as the number of columns in your second matrix. All right. If these two things are not the same, then you cannot multiply. Now, normally, so what we say for multiplication of numbers, we say that it is commutative. 2 multiplied by 3 and 3 multiplied by 2. They both give you the same answer, right? But matrix multiplication is, most of the time, you have to assume that it is not commutative, right? Okay. Can you, yeah, all right. This question is remaining, so I will come back to it. Okay. So, all right. So now, let's say if we try to switch the two matrices. So the first thing is maybe the multiplication itself is not possible, right? So if I say that if I'm multiplying it in the opposite order, so I'm saying the first matrix now becomes of the order n by p, and then I'm multiplying it by m by n. Now, this is only possible if p is equal to m. Only then can you multiply. And even when you multiply it, the dimensions of this matrix is going to be n into n. So unless m is equal to p is equal to n, the dimensions of the matrix are not going to be the same. So most likely they are different matrices. Now, let's say in this case, all m, n, p, they are all equal to 2. But still you would see, I'll show you what this multiplication is. Most likely still the multiplication is not going to be the same. All right, you would still see that the two results, the two values, they are not the same. So we would say that matrix multiplication is not commutative. Okay. Now, how do you multiply these matrices? Okay. All right. Okay. So how do you multiply these two matrices here? Okay. So now you know that the resultant matrix is going to have these dimensions. Okay. So for this example, I will have 4 in the output matrix, right? So I have A, B, C, and D. And the other matrix has W, X, Y, and Z. Okay. So what I'm going to do is, for the first position, so this is basically first row and first column. So what I'll do is, I will multiply the first row with the first column. First row of the first, so first row, first column. So first row from the first matrix, first column from the second matrix. So what I'll do is A with W and B with Y. Okay. Now, can you tell me what is the index of this element here? Which row, which column? this one. One comma two, right? So first row, second column. So now what I'm going to do is I will say first row and second column, right? So this is going to be ax plus bz, right? Okay. Now this has the this is element is 2 1. So I'll take 2 and 1, right? So cw plus dy, and then finally I have 2 comma 2. So I can take this. So it's going to be second row, second column. So cx plus dz. All right. So I now have my 2 by 2 matrix, right? So now this is not entirely essential for this course because mostly, as you would have also seen in the assignment, and we'll also check a few questions here, that so whenever you are asked, so the main idea for asking any matrix question is not for you to calculate the resultant, like the answer of the multiplication, but how it's going to be done, that is more important from the point of view of this course. But it's just so that you have a little, it's forms a base for you to understand it better. So this is there. Online you will have tons of resources available on this. So you can always give it a try. All right, take any, randomly make any two matrices of any dimensions. Don't go for very large ones, and then try to see if you can multiply them. All right. So this is matrix multiplication. And just one more thing. So let's say if I have let's say I have an equation like this. Okay. So or maybe actually wait. Mm, so let's say okay, so let's say this is the equation. I have this equation. So now what if I want to find out the value of c? What I'm going to do is I need to take this y below, right? So basically what I'm doing is I'm doing 1 by y into a. So for normal numbers, let's say y is 5, once it goes on the opposite side, it becomes 1 by y, 1 by 5, right? What about matrices? What if it was something like a b is equal to m? I'm using capital alphabets to denote matrices. So let's say if I actually want to find the value of a, I have to take b here, right? Or the opposite way. So if I want to find b, I would say m multiplied by a inverse. Let's say it's something like this. So whatever it is, I want to take a on the opposite side, right? So that is what inverse means. Now there are rules about finding the inverse, so which is not something we are going to go right now in the course. So that we'll see how to find out the inverse, but how you're going to do it by hand, there are different rules for it. If you're interested, you can definitely read about that, but I just wanted to tell you that this is why you would need to find the inverse of a matrix. Okay, and this will come when we come to that point. Okay, so now there are a few things about matrices that we can just take a look at. Okay, so we'll start off. So now so once you have a matrix, so let's just start by making a matrix. Can you tell me, if I want to make a matrix which has 2 rows and 3 columns, whatever numbers you want, can you tell me what is going to be the command for it? I want to make a matrix M. um, what's the function I write? What's the command I write? to make a matrix. I want to create a matrix here in R. You all seen the videos, you know that, right? Matrix. And that's correct. So just always try to have the habit that you enclose the parenthesis after it, right? You have opening and closing bracket, because matrix by itself, uh, it's not the function. Yeah. Oh, that's great. Good. Okay. So 1, 2, 3, 4, 5, 6, 7, n row 2, n call 2, and by row is true. So now you have 7 things to fill, and n row n call 2, 2 only means it should be 4 elements, right? So let's try and see what this gives us. Okay. Let's see if it's going to, and it's going to be a comma here. Yeah. Okay. So now you see what it does is it gives you a warning. Data length 7 is not a submultiple or a multiple of the number of rows, right? So you see it only filled it this. So yeah, it filled it by row. So 1, 2, 3, 4, that's correct. But it left the last 3 numbers, which makes sense. So just for understanding, I would like to have 3 rows here. So I'm taking 6 elements and all. Okay. So this is what the matrix is. 1, 2, then next row 3 and 4, next row 5 and 6. Okay. Now, so as of now, so now these two functions, row names and call names, they can be used to both obtain the current value of the row names and column names, as well as to assign new row names and column names. So if I write row names and M and I run it, okay, it says null right now. And if I write column names also, okay, why does it give null? Okay, anyway, so by default, these are not row names and call names, which is why it gives us null right now. So now if I want to assign row names and call names, what I'm going to do is, so I am going to write this, and let's say I want to assign. So I want to assign. So now I know that I need to have 3 names. So I will make it into a form of a vector. So C, and let's say I'll just write row 1, row, and since these are names, so I will have them in double quotes, right? Double quotes are always for names, strings, as we call them, strings or characters. Row 2, and then row 3. Likewise, for call names, I am going to write call 1 and call 2. Yeah. Okay. So I'm going to run these two. And now if we take a look at M again, so you can see now you have these row names and call names here. Okay. All right. And now, so here, this was a matrix we made, which has unique elements in a particular, whatever order you wanted. Now, instead of this, if we would have just written a single number, okay, let's say, okay, if I would have just written 3 here, so what it's going to do is, it's going to make a matrix with all the elements as that single number. So that is also fine. Okay. So it's the same element throughout that matrix. So you can do that. Okay. All right. Now, so next up, we have the option. So now, whatever matrix you see, so all elements which are at, which have the index n comma n, that means first row, first column, second row, second column, third row, third column, these are called diagonal elements. All right. Can you again explain? Which one? Row names or the same element matrix? Divya, which one are you talking about? Both? Okay, all right. Okay, so I let's try with this. So I made this matrix M. All right. Now by default, when I have just made the matrix, I get it something like this. So the row names, they're not really any names right now. They're just placeholders 1, 2, 3. And here also is just V1, V2, but there's no name particularly assigned with it. Right? So now what I will do, I want to assign as some name because it's not easy to remember. Let's say if instead of 3 or 2 columns, if there would have been 500 columns, so I can't remember first column is this, second column is this, third column is this. But if I give it some name, let's say it is a relevant name, I say one is Jean, one is count, one is something, age, whatever. So that becomes more simpler to access, right? So I would like to give it some name. So to give it a name, so what I do is, so again, what this line means, the right hand side values, which is this one, you assign it to the thing on the left hand side. So right hand side, I have made values. I have given names, which I have, written down the names that I want to give to my rows. So I say, so this vector, all right, if I just run this, it's just these 3 values. Now you assign these 3 values to the row names of M. So you have to sort of try and read the statement. Assign the values row 1, row 2, row 3 to row names of M. Yeah, so you can do that. So here actually row 1, row 2, it's not required you write this. So as and when the use comes, there are a lot of examples, a lot of ways of doing this, but it would be very difficult to go into that right now. So let's say instead of I'm writing row 1, row 2, I'll just write gene 1, and then maybe it was gene number 10, and maybe this was gene 22. All right, let's say this is what it is. So now so what I'm doing, I'm assigning this. Yes, all right. So I will, yeah. Okay. So Yuvashri, what you are writing, it's very much possible, right? I will just give you a hint. So it's would not be possible to go into it right now. It will be lot of things to discuss then. But just remember that these names are names, right? As in they're strings. So when you're writing row 1, that is whole of it is a string. But when you're doing the function 1:3 or 1:7, like you've written, um, that is going to be on numbers, right? A character 1 colon a character 7 does not make sense. A number 1 to number 7 makes sense. So what is the way that you can combine numbers and characters? You can think about that. You can keep this question with you. If sometime later we get some time, then I can show you that. Otherwise, you can give it a go. You can search for it online. Yeah. And then saving the matrix that we do as a CSV file, this I'll just let you know. Please remind me if in case I forget before the session ends, but I think this is worth discussing. All right. So if I have assigned this, and let's say in column names, so again doing the same thing, assign the names on the right to the to where do I assign it? That's written on the left. Assign it as the column names of M. So if I run this also, and if I see this, so now I have these values. And this is what I was telling you, that both call names and row names can be used to even look at it. Now, if you want to look at it, you can just see. So you remember earlier when I had run this, it's saying there are no names for it. So by default, the call names and row names, the values you see 1, 2, 3 and V1, V2, they are just sort of there to visualize. They are not really values. But now you have given those names, right? So these two functions, they can be used to both obtain the row names and call names and also to assign row names and call names. All right. Okay. And then we were talking about, so you can have, so matrices. So normally you talk about two kinds of matrices. One is a square matrix, wherein, so we said that the order of a matrix is m by n, number of rows by number of columns. If the number of rows and number of columns is equal, you call it a square matrix. Otherwise, you say it's a rectangular matrix. One can be larger than the other. So now specifically, so before going to square matrices and all, so the other thing is, if somehow you just want the same value in all the positions of that matrix, so this thing, this data input, right? So here the data was as many entries as the number of row multiplied by column, right? As many elements there should be. But if you're just writing the same, this just a single digit, so it's going to fill that everywhere. So it's going to be looking like this. Okay. All right. And then, yeah. So then, what are diagonal elements of a matrix? So all the elements where the row index and the column index of the element is same. So 1 comma 1, 2 comma 2, all of that, that all becomes your diagonal elements. And a diagonal matrix means that only those diagonal elements have a value which is non-zero. Everything else is zero, right? So diagonal, so non diagonal elements are zero. Everything else may or may not be zero, but typically it's non-zero. So now if I ask you, so what, so yeah, let's say in this one, which ones are the diagonal elements here? Like, can you just tell me which number? Is this a diagonal element, this one, this, which of the ones are diagonal elements? 1 and 4, right? Because the index here is 1 comma 1 and here it's 2 comma 2. If you go to 3 comma 3, it becomes outside your matrix, so it's not there. So in a square matrix, if it's like a 4 by 4 matrix, you would have 4 diagonal elements. But in a rectangular matrix, you will have only as many diagonal elements as the smaller of the two. Number of rows, number of columns, right? Here you have 2 columns, 3 rows. So the smaller of the two is 2. So you have 2 diagonal elements. Okay, so anyway, so if I ask you to make a diagonal matrix, so basically, let's say if I want to make a matrix which looks like, I'm making a 3 by 3 matrix for now. So 1, 0, 0, 0, 1, sorry, 0, 1, 0, 0, 0, 1. Let's say this is how I want. This is a diagonal matrix, right? Let's just, yeah. So let's say this is what I want my matrix to be. So so how should I go about it? So if I use the same function, like this matrix function, I'll have to do a lot of thinking, right? That first position, then second, third, I need to put 0, then fourth also 0, then some value like this, right? So it will be cumbersome. So you can do it. It's not impossible, but the better option is to directly use the function diagonal. So if I write diag, and so here, so in diag, it's going to be matrix data 5. So if you write this thing, data is 5 or data is 1, then all the elements are going to become 1. But what we want is the non-diagonal elements, they should be 0, right? Like this, right? So what you're saying here, if I write this thing, so I get all 1. But now instead what we will do, let's say, right? So if you see this, right, or for that matter, I can do 1 comma 2 comma 3 also. Sorry, yeah, right. So you see this. So I said that I want to make a, here I am making a 3 by 3 matrix, and so I know that there are going to be just 3 diagonal elements. So I gave the values of the 3 of them, right? I could have also, let's say I'm making another matrix and I'm making it like this. So again, in the lower of the two, that's going to be my number of diagonal elements. So this also is a diagonal matrix, right? It just has 3 diagonal elements. All right. So that is how the diagonal matrix can also be made, right? So you can also make, so it's not just required that you have to have square matrices. So diagonal matrices are also possible. Yeah. And yeah, so like we just discussed, so again, just for sake of completion, we can have what one of you mentioned. Oh, so okay, by the way, do you see this? If I give the name f here to the variable, it turned yellow. Can anybody tell me why that happened? Any idea? Do you remember anything from the lectures that mentions something, what capital F stands for? No? So capital F stands for false. Yeah. So it says that, so yellow basically means it has R identified it as something important. So we won't use that. So I'll just use a different one. So G here also. So this is also a diagonal matrix, and so you can have a single element in all the diagonals. You can have different elements and so on and so forth. Okay. All right. Now, the next thing we talk about transpose of a matrix. So transpose, you might have come across this term while you are working on Excel also. So basically you are interchanging the rows and columns. So if your matrix initially had, it was a 2 by 3 matrix, after transpose, it becomes a 3 by 2 matrix. And you denote it when you are writing it on notebook, you denote it with a superscript T. And here it's a function with T bracket. So we can take any example. So I think the best one would be this matrix M itself, right? So you know what M is, and then let's say I'm assigning N as this one. Yeah. So you know this is M, right? 2 columns, gene 1, gene 10, gene 22, that's the rows. So if I assign the transpose of M as N, now this becomes your matrix, right? 1 and 2, here you see, I'll just close these, right? So the first row was 1 and 2, where it said gene 1. Now the first column became gene 1 and 2. And right, likewise. Okay. So yeah, so this is transpose of a matrix. And now in matrices, you very often would like to find the sum of each row, right? So basically this thing. So if I want to find sum, so I want to sum the first row, basically 1 plus 2, and then 3 plus 4, and then also 5 by 6. So I am doing sum of each row. So row sums. And then, or maybe if I want to find the sum of columns, so call sums. So 1 plus 3 plus 5, that's for the first column. 2 plus 4 plus 6, that's for the second column, right? So what I can do here is row sums of M, and likewise call sums of M. So Let me just have the matrix here, right? So how many elements will I have? What is going to be the length? How many elements am I going to have in this? In row sums?
One.
Your voice is breaking. Can you say that again?
3 elements total.
3 elements, right? Yeah. And call sum should have
2 elements.
2 elements, right? So this was something which was very confusing for me initially. When I started, I was always confused in row sums and call sums, right? So row sums, you can see here, you get 3 elements, right? 3 of them. And you have the name of the rows along with it. And for call sums, you will have just 2 of them, right? Not this one, right? 1 plus 3 plus 5, that's 9. 2 plus 4 plus 6, that's 12. Yeah. All right. So this is as many elements as the number of rows, which makes sense, right? And this one will have as many elements as the number of columns. Okay. And again, now row means and col means, it's basically same as dividing the row means by the number of columns, or no, by the number of rows itself, right? So you got row sums was 3, 7, and 11. Now if I write row means, I will again have 3 elements and I am dividing, yeah, so it's dividing it by the number of columns. So why is that happening? So yeah, so basically it's sum of the row, right? So 1 plus 2, that's 3. And you want to find the mean. So mean of these two numbers. So how many numbers are there? There are 2 numbers. And why are there 2 numbers? Because there are 2 columns. So basically, I will write something here. Let me know if that's clear for you. So if I write row means of M is same as, I'll just do it as a comment, as row sums divided by n col, and likewise col means the same as all sums main row. Yeah, do you think this makes sense? So I'll just clear this for now. So we have these 2 things as our row sums and col sums, sum of values across each row and across each column. And then we also have the means and for the rows and the columns. So they have as many elements, right? Now, if I write this, row sums divided by the number of columns, n col means number of columns, right? So if I write this, I should again get row means, right? I get that. And col sums by number of rows, I should again get 3 and 4 as the answer. Does this make sense? Yeah, is it fine?
Yeah, sure.
Yeah, all right, okay, great. So okay, so this was the end of the first lecture. In the next one, how to get the sum of a particular row. Okay, good question. Can you think about it? So the first thing, so when you want to get the sum of a particular row, think about it. How would you do it if you are doing it manually? So maybe there's more than one way to do it. So can you think how would you proceed for it? So you have this matrix with you, and let's say you want to find out the sum of the second row. Okay, so what Do you think, like, if I ask you to calculate, you're going to tell me it's 7, right? How did you find it? What did you do? Can you explain your thought process? Uh, can you say that verbally? Because it's a very good question. It's going to clarify a lot of things. Anybody would like to try? Ah, okay, great. Both of you are correct. Yeah. So that's right. So you want to find the, so what you did here, sorry. So you said you want to find the, so here basically what you've done is, so we solve it from the inside first. So what you wrote here was M, and in bracket you wrote 2 comma, which means you take the second row. So M 2 comma. So you first filtered out your row of interest, and this is what it was. And then you want to find the sum of it. So now you enclose this row sums. Okay. Now the thing is, if you take a look here, this is no longer a matrix, right? This becomes a vector. It has only one dimension. So instead of doing row sums, you can just write sum, right? That's okay. Yeah. And what the other option is M 2 comma 1. So this multiply this, these two, you are individually specifying the indices of each element that you have to add, which is also correct. This thing would only be a little tedious if you had many elements in that row. So then it would become difficult. So this one is going to be better, right? So sum, and then you're just writing your row index of interest. Can you tell me if there's one more way you can do it? So what you did here was you first specified which row you are interested in, and then you said sum it up. Can I do it the opposite way? Can I first find the sum, and then I say I am interested in the second value of that sum? Can you tell me what would I write for it? I'm first I'm first finding out the row sums, and then I'm going to say 2, like the second one from it, right? So that, right. So row sums, and just after it, so what you can do is, let's say you saved this. So row sums we found here, right? This one, right? So let me just, yeah, great, perfect. You're all, so I'll just write. So let's say, how to find the sum of a particular row. Let's put it here. Okay. So we have a lot of options. So one, we said sum of M 2 comma, right? So just a comment here is that using sum instead of row sums, and you understand why, right? Great. That's perfect, right? The other option, which one of you mentioned, this one is 2 comma 1, and then you add M 2 comma 2, right? So just to see all of this is working, this one we saw, this one, oh sorry, 2 comma 2 here. Yeah, this one's also there. And the last option that you said, so first thing we are doing is D is the row sums of M, and then I don't actually need to put it in comments, just this one, right? And then I'll say D, take the second element of D. Now you see D is actually no longer a matrix, right? So the small d, it's a number, it's a list, right? It has names associated with it, but it's a list. And then I just take the second element from it, right? Which is 7, right? So yeah, perfect. Great, all of you. Yeah. And I'll just say there's just a smaller notation of this, but so this is going to come over with time for you. This thing. This also, it's doing the same thing, just in one step. But yeah, right? So all of these are the ways to find the sum of a particular row. All right. So good job, everybody. Great. Okay. So now we come to the next part. Yeah, sorry.
Yeah, sorry for the interruption.
Yeah.
Later, if you want that value, if you want to add that value to the matrix earlier, what we have built or designed, how to do it?
Say that again. I did not understand.
For example, in M matrix, now you have calculated the sum of one row.
Mm-hmm.
Example, one row or one column, any one, you found a sum. Then
Mm-hmm.
later again we need to add that number in a next row in that matrix. Example, mean of all. Sorry,
What do you mean by adding it?
like a C bind, R bind we will do, right? For
Uh-huh.
adding a next, inserting a
Uh-huh.
row for that
Uh-huh.
matrix.
Yeah.
Like that, if you want to add a single element in that row, how to do it?
Okay. So you cannot add a single element. So if you want to add something in this row, let's say after 3 and 4, you want to add an element here, you will
Yeah.
need to add something here and here also. Right? Because when you say if it becomes like a 3 by 3 matrix, all the elements have to be there. A single element cannot be added. You can have NA on that. We sometime this mention came, right? NA, not like NA, like a just a placeholder. You that we can do. So we'll just come to C bind and R bind in a while. So let's try it then. Yeah. But yes, for a matrix, it has to be it like the rectangle or the square has to be made completely. Okay. All right. So, all right. So now here you know what the order of a matrix is, and this also you can try and find with this dim command, right? So that will tell you. It will first give you the number of rows, then it will give you the number of columns, and this we have already seen how to access, right? This is how you're accessing a particular element. This is how you're accessing a row, and if it's after the comma, then you're accessing a column, right? So basically, so I'll just mention something here. So if I write this, and if I'm writing, let's say this thing, versus if I'm writing, let's say these are the three things I'm writing here. Let me run the three. Okay, wait. How many do we have? Three rows and two columns. Maybe it's like this. Okay. So, okay. Now, these are the three things I did. So here I'm accessing one element. Here I am accessing one row. And here I am, whatever I'm accessing, I'm getting a smaller matrix. Right? So, right? So you are, so all of these three things, they are possible. Right? You are accessing an element here. Here it's a vector. And here it's another matrix. It's a smaller matrix. All right. So this is all you're clear with. Okay. Now, if we talk about what all operations can you do on a matrix, so simpler ones, you can add a matrix to a scalar, or you can add a scalar to a matrix. So again, let's say we are adding 2 plus m versus if we write m plus 2. Do you think it's going to give me the same answer, different answer? What is it going to be? By the way, whenever I'm clearing the screen below, I'm pressing Control L. That's the shortcut for clear. Just it's easier to visualize when there's not a lot of things happening here. Okay, so I'm adding a matrix to a scalar or adding a scalar to a matrix. So here in this case, they both give me the same answer, right? Because what is happening is that scalar is getting added to each element of my matrix, and when it's happening at an element level, it's the usual addition. So that's commutative, right? You are adding 1 plus 2 versus 2 plus 1. It's the same thing. And the same thing goes for multiplication also. But now, of course, when you're talking about subtraction and division, they themselves are not commutative, right? So for example, if it's 10 plus, let's say 10 minus m, and then m minus 10, right? So of course, these are going to be different because subtraction itself is not commutative, right? So this is there. And same is the case with multiplication and division. Okay. Next up, we talk about matrix addition and matrix subtraction. So now here, if I say now, the important part about matrix with a matrix addition is that now these matrices have to be of the same order, right? So if one of them has the order, let's say m cross n, then the other also has to be m cross n. So here, let's say, so we have this matrix n with us. So I'm making another matrix. Let's say it will have the same order, right? So we know what the order of this is. So it has, I'll just copy the command from here. And I'll just change these values. So let's say I'll write 7 to 12, right? So m is there. So, okay, right? So this is m and this is m2. Same order, right? Now I'll write m plus m2. I can also do m2 plus m. And then I can have m minus m2. And then I can have m2 minus m. So which of the two are going to have the same value?
M plus M2, M2 plus M.
Yeah, these two should give us the same thing because, so basically what is happening is first element here, so first row, first column gets added to this thing. Now whether 7 gets added to 1 or 1 gets added to 7, it's going to be the same thing, right? Likewise, 2 here is going to get added to 8. And it's going to be the same thing here, right? So addition is going to be, should give us the same thing, right? So yeah, that gives us the same thing, right? Okay. And the thing is now, both the subtractions are possible, right? So you can see here, both the subtractions, they are happening, but it's just that subtraction by itself is not commutative. So matrix subtraction is also not commutative. Okay. Now, right? So this, okay. So this was already written here. Okay. So this is there, right? Yeah. So the two matrices also have a particular order and the output also has the same order, right? So you're not adding any new row or new column into it. Okay, fine. Next, we are going to come to matrix multiplication, what we just saw in the PPT a while back. So here, now the two matrices, they need not be of the same order. In fact, sometimes being of the same order will not work, right? So a 2 by 3, or like in this case, a 3 by 2 and a 3 by 2 matrix cannot be multiplied, right? Why can it not be multiplied? because this thing is not satisfied, right? So now typically we would assume that matrix multiplication is not commutative, and let's say we take some example here. So I'll start off with M, so which is this 3 by 2 matrix, and let's say I want to have a this we know, right? N is there. So let's have another matrix. We'll call it M3. And so can you tell me what should be the number of rows, number of columns? Is there a like is there a rule? So what should it be? So the dimensions of M is 3 and 2. So what do I need to fix about the other matrix that I want to multiply? It doesn't have to be just the opposite of it. So the thing is that let's say I what I want to do is multiply M with M3, and the multiplication is through this percent asterisk percent. So M3 is coming second. So the number of columns in M and the number of rows in M3, they need to be the same to anything, right? So that is correct. So n row here is 2. N col can be anything. So let's take 4. And which makes it that the number of elements are going to be 8 here. So let's have this like that. Okay. So now if I multiply, so I'll just call it out M, or maybe I don't need to save it as such. So, okay. So before we see the result, can you tell me what is going to be the dimensions of this? So this has 3 by 2, and this has 2 by 4. So it should be
12.
Good. Right, so it should be 3 by 4. And is it 3 by 4? Yes, it is 3 by 4. Right? So again, this also multiplication you can do by hand, the same thing that we saw there, but it's just you will have to do it. You'll have to do the whole thing 12 times, right? So that's all. But you can see now if I say M3 percent start percent M, what would be the dimensions of this?
I think it won't get multiplied first.
Good. Yeah. Right. So if I write this, it says, so the way it's written, it's non-conformable argument. So, right. So you cannot multiply. Right. Okay, good. So this is why we normally say that matrix multiplication not commutative, because sometimes the opposite is not possible because of the number of rows and columns that are there. Okay. Now, so then we also talked about something called the transpose, right? So if I multiply M with the transpose of M, this is one way, right? So this is one way, and the other way can be, first I'll write transpose, okay, not this multiplication symbol, this one, and this one, right? There are two things I can write. So the thing is, in case of a matrix and its transpose, so let's say the matrix here, my matrix was 3 by 2, right? So 3 cross 2, and you are multiplying it by a 2 cross 3 matrix. So that's possible. Likewise, in this case, I'm first saying the transpose. So 2 cross 3, and then I have a 3 cross 2. So this is also possible. But now the result in both of them is going to be different. Here I'm going to get a 3 by 3 matrix, And here I'm going to get a 2 by 2 matrix. This itself means matrix multiplication, yes. Yeah, the percent star percent, that's the notation for matrix multiplication, right? So now you see that both of these, they are possible because of the nature of the values itself. But now in both the cases, we are getting the resultant matrix to be a different order itself, right? So if I have this one here, I get a 3 by 3 matrix, and by this one I get a 2 by 2 matrix, right? And just another function, so this you were sort of doing manually, and if instead I just write cross prod and I write m, so this is also giving me the second one. It's giving me transpose multiplied by the matrix, not the first one, but the second one. That's also giving me. So that's also just one more option available for you. Otherwise, the manual thing, that's always the option is always there. Okay. Okay. Now we come to that C bind and R bind thing. Okay. So now I have this matrix with me. I want to add a few rows below this, or let's say, let me just clear this for now, or maybe let it be. Okay, how do we go about it? So I'll just define the matrix again, because we'll take a few examples here. Yeah, this is the matrix. So I define matrix M. It has 3 rows and 2 columns. I have a matrix M2, which, let's say, I say it has 3 rows and 3 columns. So I need to have 7, 8, 9. And I have M3. Maybe I should call this M3 so that it's not confusing. And I will say it has 2 rows and columns. Do we have a question? We can take new matrix, one with X and another with Y. What X and Y here? Okay, so we have this matrix, right? And we have this one 2 by 2, and this is a 3 by 3 matrix. Okay, now I want to, let's say I want to combine these matrices in some way, right? So, okay, earlier, okay, no worries. Okay, all right. So now the thing is, if I want to, so if you take a look at M here, so we have 3 rows, right? And now M3 also here has 3 rows, right? So what I can do if I want, I have these 3 rows and I have another matrix which also has 3 rows. So I can just add this side by side. So these 2 columns, and then I'll just add these 3 columns next to it. That I can do, right? Because they have the same number of rows. To add something side by side, now, if I'm saying, so if I do this thing, so if I say, if I want to add column next to the column, right, the number of rows must be same. So that I can do with M and M3. So you see what happened? This part was M, this part was M3. They both had 3 rows, so I just added them side by side. And here the order matters. If I write M3 and M, This will also work, but now what I'm getting is first, this is my M, and then this, sorry, first this is M3, and then this is M, right? But it works. This is how cbind works. And likewise, if you want rows here, if you want to have, as in, if you want to increase the number of rows here, the number of columns have to be the same, right? So this has 2 columns. Anything that you add below should also have 2 columns. So like this has 2 columns. It could have any number of rows in it. You'll just add the whole chunk here. But this also has 2 columns. This also has 2 columns. Okay, so what you can do is you can say rbind. Rbind means bind rows, rows, and then rows. You're setting rows below the rows, right? So here it's M and M2, and the other way could also be M2 and M, right? So if you see this thing here, right? This one. And so here you first have these 6 elements, right, from M, and then these last elements from M2. And likewise, you could have the other way, M2 followed by M. Now, we were initially talking about, so let's say if I wanted to add an element here, right? So I wanted to add, so what I can sort of suggest something in this. Okay, so first of all, let's say I want to add some elements here on the right side of this matrix. Is it going to be cbind or rbind?
Cbind.
Cbind, right? Because I'm binding it column to column. So that's going to be cbind, right? Now let's say I want to bind. So what I want to do is I want to sort of, I'll just write it like this. I want to bind row sums of M to M, right? So what I want to do is, no. So now you think about it. When we say we have, sorry. Yeah. So when we say we have row sums, we have sum of each row. So we have 3 values here, right? 1 plus 2, 3. Row sums of M. We have these 3 values, right? Imagine this as a column, 3, 7, and 11. I want to add these 3 values here. So what I'll do is, I'll say, as you were all saying, since I want to add a new column here, so I'll say cbind. The first one remains M. And the second element here is going to be row sums of M. So if I write this, and see, this was my original M, and here I have added the row sums. So in cbind, you always have 2 arguments. You're binding at least 2 things, right? Cbind the first thing, comma the second thing. So here you need to have the first thing is that matrix, and then you have this. Can you now tell me if instead of adding 3 elements here, I wanted to add the sum of each column below it? Just think about this thing. Maybe I won't show you. Yeah, it's rbind, but what are we going to write here? Yeah, I'm hiding all of this. Yes, that is also what you can do. All right, good. So now this thing is, so what you just wrote here. So let's, I'm so sorry. Why did this not get copied? Yeah, right? So here you got this. And if I'm running what you wrote, here also I got this same thing. So that's good that this is also working correctly, right? Because it could be sometime when you want to add on a column of your own, some values of your interest, right? So that's also working. And now if I want to bind all sums, so sum of columns of M to M, I'll do exactly what you've written here. I'll just copy this, paste it here. Did it work? No, it's not working. Why it's not copying? Yeah, right? So now, did it work? Yeah. 1 plus 3 plus 5, that's 9. 2 plus 4 plus 6, that's 12. Good. Yeah. So I think this makes C bind and R bind much more relevant. So thank you for asking this question. Okay. Okay. Just give me a minute. All right. So with that, we come to the next thing, which is finding the inverse of a matrix. So this I've just told you why would you need to find the inverse. There are applications in maths where you would want to find the inverse of a matrix. So basically, what you just need to do is write, solve, and that matrix. And what you get is the result, but it's an important thing that the inverse is only defined for square matrices. Okay. So just to understand, let's define a square matrix. So matrix data is equal to, let's say, I'll just write minus 2 to 1. These are 4 values. N col is 2, n row is 2. Did I write? Yeah, n row is 2, and let's not write by row. That's understood. M3, I think oh yeah, M3 is a square matrix. Okay, never mind. Yeah, so this is n, and then if you write solve n, so you get this, right? That is n, and that is your thing. Also, of course, like you mentioned, solve M3, that's also a square matrix. What happened on this? In case you want to add 2 columns with the help of vector, okay, I will come to this. Let me just see what happened here. Okay, yeah, I don't know why this is not working. So I'll just mention something here. I think that is why this is not working. So there's something called a determinant of a matrix. Okay, that determinant of the matrix must be non-zero. Okay, I will just quickly recap this. There's been a slight confusion. Okay, so we just saw here, right, that there are cases where you might want to find the inverse of something. Inverse basically means 1 by that value, right? Inverse of 5 is 1 by 5. So inverse of a matrix is 1 by that matrix, but that's not how it's written. So you want to find the inverse. And that is what the solve command does. That finds the inverse. But the special bit is that the inverse is only defined for square matrices. And the second thing is the determinant of that square matrix must be non-zero. Okay. So like we discussed, like I just had a dummy example here, n. So this is n, minus 2, 0, minus 1, 1. So if you write solve n, this is what you get. So this is the inverse of that matrix. Now when we did solve another square matrix that we had, M3 here, this one is also a square matrix. It said that error in this system is computationally singular. And so I think this means that the determinant was 0, but so negative numbers are not there in M3, right? So see, M3 does not have any negative numbers. So the error came in M3. In n, it's fine. For n, it worked, right? This is n, this is solve of n. So that did not give an issue. So, so I think that is what it is. Solve, it only gives you inverse, and the inverse is only defined for square matrices which do not have a zero determinant. Solve is only for a matrix. So inverse of a number does not make sense, right? Inverse of number, 1 by that number. But inverse of a matrix is something special, so that is where the solve thing comes. Okay. So this is there. And okay, so I'll just mention something. This was not covered in the lecture, so I don't think it's of a lot of importance. But so if I just say, so let's say again, this is your matrix M, our ever favorite matrix. So this has 3 by 2 dimensions. Now let's say if I have a vector V, vector means same single two, like just a single dimension thing. Let's say if it has it just has 2 elements, 3, 4. So this has a dimension of, you can say it has both 1 cross 2 or 2 cross 1 dimension, depending on how you are using it, right? So you can also multiply this, right? Ideally, it should be possible. You have a 3 cross 2, and with it, you have a 2 cross 1. So these two numbers are same. So you can multiply them, right? So multiplication is possible. You have a capital P in the first line and a small p in the second line. Yeah. So R is case sensitive. So if you're defining the variable with the capital P, it has to be capital, both the places. Okay, so this is also possible, but let's not get into it too much. But okay, so let me just tell you one more thing before we come to this part. Okay, I just add it here itself. So now, this one. So now we talked about matrix multiplication, right? Now let's say there is a vector V and you have a matrix M. You multiply this, okay? So what you do is, this gives you, so what it does is, I hope I'm doing the right step. Yeah. So this is, let's say, M by N dimensions. And this is 1 by M dimensions. Now you get 1 by N dimensions. And if M is equal to N. So basically, let's say you have a vector which has 2 elements and you multiply a matrix which is a 2 by 2 matrix. So the resulting matrix, whatever that matrix is, sorry. So you're going to get another vector. Let's say you get W. Okay, this would also have dimensions 1 by 2. Just tell me if this part is clear, right? So we talked about, so consider vector to also be a matrix with just 1 row or 1 column, right? So this is a vector, 1 into 2. So it has, let's say it has 2 columns in a single row. And then you have a matrix which is 2 by 2 matrix. When you multiply this, going by the rules of matrix multiplication, what you're going to get is the resulting, the output would have dimensions 1 into 2. So this also becomes a vector. Now let's say you are able to write this vector as 3 times of the original vector. Let's say the original vector v was 1, 2, right? And let's say w is actually equal to 3, 6. So can you write 3, 6 as 3 times 1, 2? Right? This is same as 3 times 1, 2, isn't it? We saw in scalar multiplication, scalar with a matrix, right? So now when something like this happens, so what you did was, yeah, all right. So what you did here was you multiplied a vector with the matrix and you got the same vector back, but some times of that vector. Okay, so then if such a thing happens, then this matrix, for this matrix M, you say that this vector V is called the eigen vector, and this value 3 that you have, it's often represented as lambda. Yeah, the Greek letter lambda. This is called the eigen value. So this just simple. So there's a matrix. When you multiply the matrix with the vector, if you get the vector back, sometimes, okay, this number can be both positive, negative, fraction, anything. But if this is there, then you say that for that matrix, that vector v was an eigenvector, and that value lambda is the eigenvalue. Okay, so that is just that's an option. So now you have this function eigen. If I feed, now again, as far as I remember, it should again be a square matrix. That's what we just saw there, right? So I'll use n for now. So if I write eigen, this thing, so you see I've got these, this is my output. So it says that I have 2 eigenvalues. -2 is also an eigenvalue, 1 is also an eigenvalue. And when you say vectors, so this is also my eigenvector, and this is also my eigenvector. All right. So this is again just for your slightly just like an introduction. This is not absolutely essential to understand in depth, but you have this function. Now I'll just mention something. This is going to come handy in the upcoming weeks. So if I'm just saving, let's say I'm saving this in E. Okay. So now you see there are, so normally when you write, whenever we are writing something, it's a single value, right? This is a single chunk of value. Now when I say, when the output of eigen is actually 2 chunks, this is the first chunk and this is the second chunk of result. So here what I can do is I can access the 2 chunks independently. I'll say E, and then you see this dollar sign here. So dollar, and then you see this automatically comes up. So E dot values, and then E dollar. So E dollar values and E dollar vectors. Right? So yeah, right? So I get both eigenvalues and eigenvectors this way. Okay. So with this, we come to the end of the matrix part of this week. There are a lot of examples where eigenvalues and eigenvectors are needed. So this is something, so recently I came across this. So it's used in something called dimension reduction. So I'll just tell you in 1 minute. So sometimes you have, let's say, so I'll just give you an example from biology. So let's say there are so many genes in humans, right? Now, let's say we say that so many genes are active. So let's say 20,000 genes, they are working. But for a particular disease or something, maybe just a few of them are relevant. Okay? Or groups, certain groups are only relevant. So thing is, you cannot analyze 20,000 of them at the same time. You cannot visualize 20,000 of them, right? You can only visualize something in 2 dimensions. So there's a concept called dimension reduction, which makes use of these eigenvalues and eigenvectors. But it will be a whole different topic altogether. If you're interested, I was a TA for one other NPTEL course where, so one of my live session recordings are there on YouTube. If you would be interested, you can take a look at that. But it's a slightly difficult concept to understand. Like, so I cannot explain it to you at the moment. But so there are a lot of examples of eigenvalues and eigenvectors. Yeah. Okay. All right. So this was a biostats course. Data analysis for biologists. That's the other course. Yeah. Okay. All right. So now we don't have a lot of time, so we'll just quickly go through it. So logical operators. Okay. Now simple. So I'm just removing all the matrices from here for now. So now let's start off by some numbers. So let's define x as 20. Now, simple logical operators, there are a lot of them. The thing is, these operators, they are going to give you true and false, true or false as the result. All right. Now, simple comparison. So if you want to say, is x less than 40? Right? So, sorry. So that is true, right? 20 is less than 40. Is x greater than 10? That is also true, right? Now, if I want to say, is x greater than 20? Now, this is going to say false because 20 is not greater than 20. But now, if I write, is x greater than equal to 20? This is going to give me true, right? Because this is 20. And now we have both the options possible. Then if we say, is x equal to 20? Now you see this value versus this thing, it's the same thing, right? Here I'm assigning the value of 20 to x. Now, if I want to compare the value of x, whatever the value is, if I want to compare it to another number, then I use a double is equal to. So, single equal is for assignment, is to assign values, right? Same as this operator. But this double equal to is for comparison of equality. You want to compare if the two things are equal. So if I write this, then it's going to say true. If I say x is it equal to 5? It's going to say no, it's not equal to 5. Right? And then also we can see, is x not equal to 5? So here we were checking, is it equal to 5? Here we are saying, is x not equal to 5? Is x any other value? What should it give us? What should this line 230 give us? That should give us true. Yeah, good. Right? It should give us true. Whereas this thing should give us false. Right? Because x is equal to 20. So not equal to 20 becomes false. Right? All right. And again, now if you see here, everywhere this thing is written in capital. So true and false, it's you either write true or you write capital T, or you write false or capital F. None of the other things are considered to be true or false. Okay, So this is simple, right? Greater than, less than equal to, greater than equal to, double equal to for comparison, and not equal to for, like, this is basically not equal to. Now you can combine these things. And so there are 4 ways in which you can combine. So let's say if I just write, and like we also discussed in one of the earlier lectures, that it's always a good practice if you can enclose one group of statement in a bracket. It's just going to make it clear for you to understand, and also not have any confusion for the program to execute it, right? So let's say if I write x greater than 15 and x less than 25. Okay, by the way, do we all know the truth table here? So I'll just quickly write it. Okay, so can you tell me if x is true and y is false? Wait, let's write this true. This is also true and false. And then this is false and true. And then if both of them are false. Yeah. So if both of them are true, then this gives us true. This also gives us true. And means both of them should be true. Only then it's going to give us true. So in all the other cases, you get false for and. Whereas in case of or, at least one of the two statements, they need to be true. So here also, here also, here also, right? So here also you get true. This also gives us true, but this gives us false. So this is called the truth table, and this is what we are going to use here, right? So this, if I just run the first part, x greater than 15, this is true, right? This is also true. Now I have true, and I want to find the and, right? So I get true. So the whole thing should return me true. No confusion about it, right? Now let me just, I'll just write it. Let's say it's this, right? So it's going to give me false. Whereas now in case of and, if I would have had or, so this is true or false. So this would give me, for or, this is going to give me true, right? So true here. Now this is how you can go for this. This is simple, right? Now we will just okay, before I go into that, there's something called this also, and something called this also. This one. So by the way, this and symbol is the one above 7, right? So shift 7, and this odd symbol is just below the backspace, or just above your enter. So shift and that key is going to give you this symbol. It's also called the pipe symbol in some ways, in some cases, but yeah, that's a discussion for some other time. Okay, so here we were just talking about single numbers, right? Now in case, so let's say if y would be 5, 10, 15, 20, right? And now if we do the same thing, but now instead we substitute it with y everywhere, right? So now this, oh, sorry, right? So y greater than 15, I'm evaluating for each of the elements, 5, 10, 15, 20. So it's going to give me false, 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 true, right? And then this one is going to give me, it's going to be false for everything. So I'll take a better example. Maybe I'll take less than 18. So there's something here. Okay. So this is there, and then y less than 18. So true, 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 and this is false. Now, again, now you apply a truth table on each of them. So false and true for and, false and true again for and, false and true for and true and false for and. So here, all of them are going to give me false, right? Whereas for this thing, here I'm getting a true in all of these cases because this is also true, this is true, this is true, this is also true. And now these two examples. So here what is happening, it's going to evaluate this one first. If it gets true, it'll stop. If it gets false, it'll continue. Okay. So let me give you another example actually for this. So wait. This is there and this is there. And then these two. So these two you understand, right? False and true, they give you false. So here you get true in the third one for and. So now instead, if I would have a double and here, so it's going to what happened here? Logical one. Okay. Oh, it's a warning. Yeah. Right. So it evaluated the first one. Right. And it stopped. And likewise, here also, it's going to go. It's giving you these warning messages, but the first one gave us true, right? So it has different uses, but for now you can just understand this notation is for the first element only, and this notation is for all the elements. And just one final thing, since we are again running out of time. So we just talked about accessing elements of a, so let's say we have this one here. Yeah. So now if I want to access the second element of it, so what can I write? I'll just write 2, right? Yes. And then only the first element. So only, so what I mean by this is, so here I had these two things, right? I had this list of true, false, true, false. I had this list of true, false, true, false. Now, if I just had this single and or a single or, it's comparing this false with this true. So it's giving me false. It's comparing this false and true, gives false. This true and true, it gives true. And this true and false, it gives false. But now, so this one was this and. But now if I had this double and, it only compared this and it stopped. It did not, it just ignored the remaining elements. Okay, all right. So yeah, so when you have a vector or a matrix, I'll just give you an example for a vector. So you can access a particular element at a particular index, right? So let's say if I wanted the second element, I can just have, I'll write 2 here and I get 10. Now the other option is I can write y, and what I can write is I'll write false, comma true, comma true, comma false, comma false. Sorry. Yeah. So now here you see there are 4 elements. I have 4 true, false things. The first one is false, next is true, then false, then false. So what I'll get, not find the function. Oh, sorry. This thing. Yeah. right? That also gave me the element 10 because it said false for the first element. Don't give me false. Like, don't give me the first element. True for the second element. So give me the second element. The third value is again false. So don't give me the third element. And here also false. So don't give me the last element. Right? So likewise, if you see here, so you got this list, right? This was also a vector. This list of 4 true, 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 true. Yeah, so this is also going to, so this is a list, right? This is a vector. So you're feeding this vector inside your numeric vector. Please also show how you save all the codes in the end. Okay, fine. So this is, so I've reached the end of what I have for today. So what I did was initially, so I'm just, so you see this star here. So I'll just press Control S. So it's going to get saved. So what I did before today's class, when I was preparing for the class, I did file, open file, R script. So it opened this R script. Okay. Now let's say, just to show, I am Control A, selecting the whole thing, Control C, copying it, and then I'll press Control V here. So I just have all of it here. Okay, everything, I have it saved. Now if I say save as, and let's say I'm writing this. So let's say I cite class 4 script. And if I save it, so this is there for me, right? Class 4 script. And this one got saved here. So this one I'm going to upload to the Google Drive. You can download it. If you have RStudio installed on it, you directly double click, it will open in RStudio just like this. So then you can execute it line by line. So and here. So here you have a list of true and false. Here also you have a list of true and false. What the single AND is doing is comparing the first element of the first list and the first element of the second list. So let's say these two, not this actually, but this false and true, this false and then this true with this true, this true with this false. But what the double ampersand was doing, it was only comparing the first element and the first element, and that's it. So it compared false and true. So false and true gives false. So it gave false. Likewise, the double or symbol, false or true, gives true. So it gave true. End of story. Right? So that is what it was. Now, I would mention just one more thing here about these things. So we were stuck at this question also. This was one of the questions in assignment 2. So where you had several of these operators, you had AND, single AND, double AND, the long notation, short notation, everything. And you were asked to find out the output of a complicated thing like this. Okay, so I will just explain this here. So now you remember when you're talking about mathematical operators, you have the BODMAS rule, right? Now, in case of logical operators, this is your BODMAS. You first solve this, then you solve this, then you solve this, and then you solve this. Single AND, single OR, double AND, double OR. And then you will be able to solve it here. So I will just start with explaining this thing here. So can one of you just unmute yourselves and solve along with me? What is this operation going to give you? First of all the brackets. Okay. So this is quickly true. Okay. Then this one is false. Okay. I'm solving it for x is equal to minus 13. Then x less than 15, this is true. X greater than 12, this is false. X equal to 17, that is also false. So what I get is true, then this or false, then this and true, then the double and false, and then the double or false. So I am going to solve this and first. So this one. So can you tell me what is this? False and true, what should this give me? false and true? False, right? So I get true or false. Then I write the remaining thing as it is. Okay. Then I solve. So I solve this. This is done. There is nothing for here. So then I solve the double AND. So false and false. So since there's a single false, okay, it's not a list of false or a list of false here. So I just solve this thing. So false and false. This is also going to give me false, right? So true or false. Now I can solve it. So then I think this one, okay, yeah. Okay, so I think I can solve this either way. So if I do it, if I solve this one first, so true or false, and this one also gives me true or false, right? Whichever one I solve first, whether I solve this first or I solve this first, right? So this true or false gives me true or false gives me true. So the answer is going to be true for this thing. All right. So this was also left from the last discussion. This is done. We've seen these examples. Okay. Okay, I don't think we have a lot of time, but I only have 1 or 2 questions today. So I think
One more question.
yeah.
Is there any command like that operator? If the whole vector is true, it has to be true. If the whole in that vector, if any element is false, then the vector that result has to come false. Is there any operator like
There,
that?
I think there is one. So there is one. I am not able to recall at the moment, but yeah, in this question, and is the same thing as single and. Can you show the question that was solved just now? This one. Yeah. This was a question in assignment 2, I think. Right, the 20th question in assignment 2. Yeah. So the question you asked about, so if all the entries in a list is true, then it should return true. So there is a command I'm not able to recall, but I think if you search online, you'll be able to find one. But yeah, like you said, such commands, they're going to be very useful, right? So if any one of them is false, you just don't proceed with that. So it is used often. Yeah. Okay. So okay. So I think this, again, you will be able to solve these questions. What is the correct output of the command row means for a matrix when this is your matrix, right? So you will be able to solve this, I guess. Yeah. What will be the output of the diagonal? This is also something we saw in the lecture in today's discussion. And this one, you know, which is the correct notation of multiplication, right? Can you tell me quickly?
Third one.
Yeah, this third one. Okay, so this is all I had. Okay, the last slide is not updated. So we can discuss assignment 3 if there are any questions that, so one of you mentioned some questions, right? Where were we? Yeah, these questions 2, 7, 8, and 10. So let's just quickly go through it. This one, right? So we are running out of time. So anyway, the session is still being recorded. If any of you would want to stay back. So So this one, it will take me a while to solve, but you use the simple BODMAS, it should give you the right answer. Yeah. Same goes for question number 7, question number 8 also. Now you know ceiling also, this one, 8. And 10-1 also, all of these 4 questions, they can be solved using the same BODMAS rule and just solving it as per the question. Give it a try again after today's discussion. In case you still think you're confused at some way, I'll try to better plan the next week's session so that we have time to discuss these questions. Still, just before ending, is there any question from assignment 2 that you would like to discuss? The 2 things that were remaining we discussed today. Right? Anything from question 2? From assignment 2?
Sorry, nothing from assignment 2. That how to solve that matrix into Excel or any other.
Oh, sorry. Yes. Thanks for reminding. Okay. So let's. Oh, where is our matrix M? Where is it? Yeah, this one. I'll save this. Okay. So the command to save matrix as a, we'll save it as a CSV file. So there is a command called write.csv. And if you see what it shows here, you focus on the first 2 elements here. So it's X, and the second thing is the name. So first one is going to be your whatever object you made here, your variable name. And the second thing here in double quotes, you need to write. So I'll write matrix M, and I'll put the, this is very important, you need to put the extension correct. So whatever is here, that needs to go here. So write.csv, save this thing as a CSV file with this name. The name has to be in double quotes. It has to be the second argument, second entry. Okay. And let me just see. Yeah. So if I write this, it's run. Now if I open my folder here, again, just mentioning, so this thing here is your working directory, remember? So we had this get working directory. This is my working directory, and you can set it through the set working directory thing, right? In set working directory, in double quotes, you just need to put a slash, and then you start going wherever you want to, right? In users, and then here, and then you just go on, so on and so forth. And wherever you are, whatever is showing here in RStudio, or whatever is showing when you write get working directory, that is where this is going to get saved. So my working directory is this week 4 22 August. So I open this folder here, week 4 22 August, and you see here you have the matrix that's saved as a CSV document. Now if I open this, here it's opening in some numbers, but yeah, so it's saved. I'll open it in Excel. So open with Microsoft Excel, and yeah, so you see this one's, it's there. Now just another thing, so here you see these 3 things, they were actually your row numbers or row names. So since we are just here, so one more thing, you can write row dot names is equal to false. So now I'll just I'm going to close this. So be very careful that if I'm saving it with the same name, it should not be open, so that it's overwritten properly. I'm running it again. So it's saved again with, I don't want to save the row names. Okay. So if I open it now, sorry, open with Excel. So now you see the row names are no longer there because I don't need that 1, 2, 3 is extra for me. Right. So this was my column names, and these are my actual entries. Okay. So, all right. So with that, we come to the end of today's session. Thank you for staying until so long. And I think tomorrow is the deadline for you to submit the assignment for this week. So don't forget. And we'll meet next week, same time, right? So we'll meet on 29th of August, 6 p.m. All right. Thank you so much. Good night, everybody. How did you change the background of Studio to black? So it is somewhere, I know I'm not sharing my screen, it's somewhere in Tools, Global Options. Search, try and look at that. Practical applications of R. So it is very field specific, right? So for bio, separate. If it's economics, it's separate. So yeah, you should be able to find some of them on NPTEL also and on other platforms as well. Should be available, but it's a big question. Yeah. All right. Okay. Thank you so much. I'll see you all next week. Bye-bye.